Welcome to the Deep Dive. Thanks for joining us. We've got some really interesting source material today, a chance to really get into the global drone industry. It's a field that just feels like it's moving so fast.
Absolutely. And this report you sent over, it's incredibly detailed. It gives us a great look, behind the scenes, not just what drones do, which is fascinating enough, but all the complexity underneath.
Like how they're designed, where the parts actually come from.
Exactly. The whole manufacturing process, the rules, who's actually building them, all that stuff.
So our mission today is basically to unpack all of that for you. We'll pull out the key insights from this source material, give you a kind of shortcut to understanding this really dynamic world.
Think of it as a guided tour through this information.
Okay, let's jump in. First off, when we talk drones or UAVs, unmanned aerial vehicles, I mean, the sheer variety just jumps out from this source, doesn't it? They seem to be everywhere, doing all sorts of different things.
It's really striking. And what's fascinating is how the form follows function. The
Hmm.
design is almost completely dictated by what the drone needs to do.
Makes sense.
The report lays out the main categories pretty clearly. You've got your multi-rotor drones. Those are the ones most people probably picture, with like 4, 6, 8 propellers.
Yeah, the quadcopters and things.
Right. And they're super versatile, great for hovering, maneuvering in tight spots, perfect for, say, close-up inspections or getting those really dynamic film shots.
Okay, the kind of photographer might use, or maybe those small delivery drones people are talking about.
Exactly that kind of thing.
Yeah.
Then you've got fixed-wing drones. These look much more like traditional airplanes.
Right, with wings.
Their big advantage is endurance. They can stay up longer and cover much larger distances efficiently. Think about surveying huge farms or checking miles of pipeline.
Ah, okay. Less about hovering, more about distance.
Precisely. The source also mentions single-rotor drones, which are basically like mini helicopters. They can lift off vertically, carry heavier stuff, and are often used for more demanding jobs.
Heavier stuff. Like maybe bigger deliveries or, I don't know, search and rescue in tricky places.
Exactly. Search and rescue is a great example. And this leads to something really cool the report highlights. Hybrid VTOLs.
VTOL, vertical takeoff and landing.
You got it. These combine the best bits of both fixed wing and multi-rotor. They can lift off straight up like a multi-rotor, so no runway needed.
Handy.
Very. But then, once they're airborne, they transition to fly like a fixed-wing plane. Much more efficient, much faster for covering distance. It's a real game changer for things like logistics or certain kinds of surveillance.
Wow, okay, so you get the helicopter's landing flexibility, but the plane's speed and range. That makes a ton of sense for, medical supplies or package delivery over longer distances.
Definitely. And the source then dives into the different scales of drones. You go from tiny micro drones, sometimes barely noticeable,
What is this used for?
often for really discrete intelligence gathering. They can have incredibly small cameras. Then you scale all the way up to these large, very sophisticated platforms.
Like the military ones.
Yeah, in the military context, you see that scale clearly. Tactical drones for ground units, then bigger reconnaissance drones. The report mentions HALAL and MAIL platforms.
Right, high altitude, long endurance.
But then medium altitude long endurance. Exactly. These are designed for staying up for, well, a very long time, watching over huge areas.
Like eyes in the sky that can stay put for days almost.
Pretty much. And then you have the big combat drones, the UCAVs, unmanned combat aerial vehicles. These are the ones capable of carrying weapons like the laser-guided bombs mentioned in the report.
Okay.
But there are also large non-combat drones too, focused just on surveillance or maybe acting as target drones for training. And underpinning almost all of them is GPS, of course, for navigation and mapping. Photography drones are just types optimized with better cameras.
So it doesn't matter if it's a tiny thing you barely see or something the size of a small plane. There's a specific design for a specific purpose. It really shows that they're not just drones, are they? It's a whole toolkit.
Absolutely. And the uses are just incredibly broad globally. On the commercial side, the report lists so many examples. Agriculture is huge, monitoring crops, targeted spraying.
Destruction sites too, right? For mapping progress.
Yeah, construction, media production for unique camera angles, delivery like we mentioned, parcels, medical supplies.
Energy companies inspecting turbines or power lines, mining surveys, public safety search and rescue, disaster assessment, even checking cell towers. It's everywhere.
It really is. And for the military, the absolute core function is ISR, intelligence, surveillance, reconnaissance, just gathering information.
But also more active roles.
Oh, yeah. Combat strikes, identifying targets, electronic warfare, acting as communication relays, even logistics, flying supplies out.
It's almost harder to think of an industry not using them somehow. Which brings us to the next big question. How do these things actually get built? The supply chain must be pretty complex.
Oh, it's incredibly complex and global. The report really highlights how, historically, China has been a major player in manufacturing key components.
What sort of components are we talking about?
A lot of the core stuff. The brushless motors, the ESCs, that's electronic speed controllers that manage the motors, the batteries, the flight controllers, the brains, various sensors, cameras, even bits of the airframe.
And the report flags this as a concern, doesn't it? This concentration, especially for the US and Europe, geopolitics and security worries.
Absolutely. Those concerns are a big driver right now. You're seeing a real push, detailed in the source, to diversify where these components come from.
So moving away from that heavy reliance.
Exactly. Looking towards places like Vietnam, India, Mexico, and also a big push for localization or onshoring, trying to bring some manufacturing back to the US and Europe. It's about building more resilient supply chains, less vulnerable to disruption, and addressing those security angles.
Taiwan gets mentioned too, right, for the high-tech bits.
Yeah, particularly for advanced semiconductors and sensors, Taiwan is critical.
But shifting production like that, it can't be easy.
Not at all. The report points out major hurdles. It's expensive to set up new advanced manufacturing elsewhere. There's intense competition. And navigating different regulations in different countries adds another layer of complexity.
The source kind of walks through the whole business process too, doesn't it? From R&D, figuring out sourcing, software development, assembly.
Right, then testing, sales, distribution, training people, dealing with all the rules. And like you said, for commercial drones, often the real value is in managing and analyzing the data they collect.
It takes a lot to bring it all together.
It really does. So let's dive into those components, the actual building blocks. What are these things made of?
Yeah, the report got pretty specific here. The airframe, the body.
Right, the structure. You see a lot of carbon fiber composites mentioned, things like T300, T700 grades. They're super strong, but incredibly light, which is obviously vital for flight time.
Makes sense. Lighter means flies longer.
Exactly. You also see metals, aluminum alloys, sometimes titanium or magnesium alloys, and various polymers or plastics. It's all about finding that perfect balance of strength, weight, and durability for the specific drone type.
Basically aerospace materials, chosen carefully.
Pretty much. Then you've got the propulsion system, the brushless motors, the propellers themselves, which are often highly optimized, and the ESCs controlling the power flow to those motors.
And the flight control of the brain you mentioned.
Yeah, that's crucial. It's usually a sophisticated microcontroller or maybe a system on chip. It takes input from all the sensors and runs the algorithms that keep the drone stable and flying correctly. The report even mentions specific examples trying to meet security standards, like Modal AI making NDAA-compliant controllers for the U.S. market.
Okay, and the sensors? This seems like where a lot of the drone's capability comes from.
Oh, absolutely. The sensors are key. You've got the IMU initial measurement unit, which tells the drone its orientation, keeps it stable. GPS for knowing where it is outdoors. Barometric sensors for altitude.
What about indoors, where GPS doesn't work?
That's where optical flow sensors come in, which the source mentions. They basically look at the ground texture moving underneath to hold position. Very clever.
Like watching the floor to see if you're drifting. Huh.
Exactly. Then there's LiDAR, using lasers to build detailed 3D maps of the surroundings, essential for advanced obstacle avoidance or creating really accurate terrain models.
That sounds pretty high-tech.
It is. Plus proximity sensors, ultrasonic, infrared just for detecting nearby objects, and cameras, of course. Not just regular visible light cameras, EO, but infrared or thermal for seeing heat signatures.
Useful for search and rescue or security.
Definitely. And also multispectral or hyperspectral cameras. These see light beyond what humans can, which is vital for things like analyzing crop health in agriculture or identifying different materials from the air.
That ties right back to those commercial uses. It's amazing how much data they can pull in.
And running all this, processing all this data are the microchips. They're fundamental for everything: control, navigation, sensor processing, communications, any AI for autonomy, power management.
And big tech companies are involved here.
Absolutely. The report lists names you'd recognize: Intel, NVIDIA, Qualcomm, AMD, Broadcom, alongside more specialized chip firms. Their processors are often at the heart of these systems.
And none of it works without the software layer.
Right. Multiple layers, actually. You've got firmware, the low-level code on the hardware itself. Then the flight control software, the report mentions popular open source options like PX4 and ArduPilot that actually manages the flying.
What about the person on the ground?
That's where the ground control station, or GCS software, comes in. That's what the operator uses on a laptop or tablet to plan missions, monitor the drone, maybe take manual control.
And then the software to make sense of the data.
Exactly. Data processing and analytics software. Programs like Pix4D or Drone Deploy, mentioned in the source, turn that raw aerial data into useful maps, 3D models, or actionable insights. And increasingly, AI software for enabling more autonomous flight and decision-making.
Plus communication systems, video feeds, FPV goggles sometimes.
Right, the data links. And the controllers themselves ranging from simple handheld remotes to complex GCS trailers with multiple screens for big systems. And powering it all, batteries. Mostly lithium-ion types like LiPo or Li-ion right now.
But maybe other things in future.
The report does hint at future tech like hydrogen fuel cells. The big draw there would be much, much longer flight times.
So you've got components potentially coming from Asia, software maybe developed in Europe or the US, chips from Taiwan. It's a real jigsaw puzzle.
A global engineering challenge, absolutely. And assembling all these sophisticated parts needs specific kinds of factories.
Right. What does a drone factory actually look like? Is it like a car plant?
It varies, but the report describes facilities with specialized areas. You definitely need clean rooms for handling sensitive electronics and sensors to avoid contamination.
Okay, like for chip making.
Similar idea, yeah. Then areas for machining and fabrication, CNC machines for middle parts, 3D printers often used for prototypes or custom jigs, injection molding for plastic parts if it's high volume.
What about those carbon fiber bodies?
That requires composite layup areas, sometimes with large ovens called autoclaves to cure the materials properly. It's quite specialized work.
So a real mix of high-tech and maybe more traditional manufacturing skills.
Exactly. Then you'll have assembly lines. These could be largely manual for complex, low-volume drones or increasingly automated for, say, consumer models. And critically, huge emphasis on testing.
How do they test them?
Flight cages for basic indoor flight tests, calibration stations to make sure all the sensors are accurate, quality control checks with precise measurement tools. The report names some typical equipment makers like Haas for CNC or Stratasys for 3D printers, just to give a feel for it.
And production capacity must vary wildly.
Oh, hugely. Making thousands of small quadcopters is a totally different ballgame than building a handful of massive reconnaissance drones per year.
Right. Okay, so they're built in these complex factories using parts from all over. But once they're ready to fly, there are rules. Lots of rules, I imagine, both for flying and maybe even for making them.
Regulations are absolutely critical to understand. The report uses the US FAA rules as a good example, but it notes most countries have similar structures: EOSA in Europe, SIAC in China, and so on. The basic idea is usually to separate rules based on drone weight, how it's being used, and where it's flying.
So, like for fun, hobby flying in the US, what are the rules?
For recreational use, if your drone's over about half a pound, you need to register it. You have to pass a simple online safety test called Trust, and then follow basic operational rules.
Yeah.
Keep it in your sight, stay below 400 feet, stay clear of airports and restricted airspace. Pretty straightforward for hobbyists.
But if you're flying for work, commercial use.
That's under Part 107 in the US, and it's much stricter. You need a remote pilot certificate, which means passing a more detailed FAA exam. There are tighter rules on altitude where you can fly, especially near airports. You often need specific authorization through systems like LAANC,
LAANC.
low altitude authorization and notification capability. It's an automated system for getting airspace permission quickly. There's also a speed limit, usually 100 mile an hour, and strict rules against flying carelessly.
What if you need to do something outside those standard rules, like fly further away than you can see?
That's where waivers come in. The report mentions needing specific FAA waivers for things like flying beyond visual line of sight, BVLOS, or operating at night. And a big recent change is remote ID.
Remote ID, what's that?
It basically requires most drones to broadcast identification and location information while they're flying, sort of like a digital license plate for drones. Helps with security and accountability.
And military drones, they play by different rules.
Generally, yes. They often operate in restricted military airspace, but they still need to coordinate carefully when near civilian air traffic.
Okay, those are the flying rules. What about rules for making the drones? Especially those chips.
Right, the report touches on this too. Making advanced semiconductors is incredibly complex environmentally. Building and operating those fabrication plants, the fabs, requires a whole raft of permits.
For what sorts of things?
Construction, operations, managing hazardous chemicals, using huge amounts of water, controlling air emissions, disposing of waste. It's a major industrial process.
And the report mentioned something about the U.S. environmental rules here, the CHEPS Act.
Yes, exactly. The GPS for America Act aims to boost U.S. chip production. Normally, big federally funded projects like new fabs would need environmental reviews under NEPA, the National Environmental Policy Act.
Wow.
But interestingly, the report notes there's language in related legislation, the Building Chip in America Act, that can exempt some semiconductor projects from those NEPA reviews to speed things up.
So potentially faster construction, but maybe less upfront environmental review?
That's the tension, yeah. Though the report stresses they still have to comply with other major laws like the Clean Air Act, Clean Water Act, and hazardous waste rules under RCRA.
And there was a specific chemical concern mentioned.
PFAS, per and polyfluoroalkyl substances. They're used in chip making, and there's growing concern and pressure for tighter regulations because they're very persistent in the environment and have potential health risks.
So it's not just about safe flying, it's the whole life cycle. The environmental footprint of making the components, assembling the drone, dealing with waste like old batteries or carbon fiber scrap.
Absolutely. It adds cost and complexity, which, loops back to those challenges we talked about in diversifying the supply chain. It's all connected.
Wow. Okay, so who are the companies making all this happen? Driving the innovation. The report lists quite a few.
Yeah, it gives a good snapshot, though it's definitely not exhaustive. You've got the big drone platform manufacturers themselves. DJI, based in China, is obviously a huge name, dominant in consumer and enterprise markets globally.
But lots of others too, focused on different niches.
For sure. You've got Parrot from France, strong in enterprise and defense. AeroVironment in the U.S., known for tactical military drones. Skydio, also U.S., really pushing the boundaries of autonomous flight.
What about some of those specialized types we talked about?
Well, there's Wingtra from Switzerland, making those VTOL mapping drones. Aerobotics from Israel with their drone-in-a-box systems for automated industrial tasks. EHang in China is focused on passenger-carrying autonomous aerial vehicles, AAVs. And Brince in the U.S. makes drones specifically for dangerous indoor tactical situations, like for first responders. It really shows the range.
Then you have the companies making the guts, the components, and chips.
Right. The report mentions Modal AI, again, for U.S.-made flight controllers. Microchip technology is another name. And then the big semiconductor giants we discussed, Intel, NVIDIA, Qualcomm, AMD, Broadcom, and Xenotech as a sensor specialist example.
And crucially, the software and service providers, making the hardware actually do something useful.
Absolutely vital part of the ecosystem. Companies like Drone Deploy, Pix4D, Skycatch, Propeller Arrow, they specialize in turning drone data into usable maps, models, and analytics.
What about managing the flights?
You've got companies like Altitude Angel working on drone traffic management, kind of like air traffic control for drones. SPH Engineering and DroneLink provide software for planning complex missions. And Auterion offers an open-source-based operating system that many drone makers build upon. It shows the value isn't just in the flying hardware.
And we also see the big traditional aerospace and defense players involved, right?
Definitely. Boeing has its subsidiary in situ making drones. Northrop Grumman builds massive platforms like the Global Hawk. They're integrating drone technology into their portfolios.
Looking at that list, it really drives home how global this industry is. Players headquartered all over Asia, North America, Europe, drawing on expertise from so many different fields.
It's a real mix of consumer electronics heritage, cutting-edge software development, and traditional aerospace engineering.
Okay, we have covered a lot of ground in this deep dive. It's quite a journey. We started with just the sheer variety of drones, different types, different sizes, all tailored for specific jobs, whether commercial or military.
Then we really dug into the supply chain, how these things are built, that complex global network, the historical dominance of places like China, and the current strategic push to diversify manufacturing, plus all the challenges that involves.
We broke down the key components, the lightweight materials for the airframes, the motors and propellers, the critical sensors like radar and thermal cameras, the powerful microchips acting as brains, all the different layers of software, and the batteries keeping them powered.
We took a peek inside the specialized factories where assembly happens, and then navigated the really important world of regulations, not just the rules for flying drones safely, like Part 107 and Remote ID in the US, but also the permits and environmental considerations involved in actually manufacturing them, especially the chips.
And finally, we looked at some of the key companies driving this whole industry. The drone makers, the component suppliers, the software developers, the service providers, showing just how broad and global this ecosystem really is.
Yeah, the big takeaway from the source material is just how incredibly dynamic this field is. It's not standing still. Technology is racing ahead. Regulations are constantly trying to catch up. And it's all happening within this complex web of global economics and security interests.
So as we wrap up, here's something for you to chew on, based on everything we've unpacked today. Considering how tangled that global supply chain is, how fast technology like AI and autonomy is moving, and how the rules keep changing, what's the right balance look like in the future? How do we maximize the incredible innovative potential of drones while still making sure we manage global security, safety, and privacy effectively? And maybe more personally, what role do you see drones playing in your life or in society over the next few years?